Welcome you all. Today we are going to discuss one more problem in a gas turbine. The question is, a 5400 kilowatt gas turbine generating set operates with two compressor stages. The overall pressure ratio is 9:1. A high pressure turbine is used to drive the compressors and a low pressure turbine drives the generator. The temperature of gases at entry to the high pressure turbine is 625 degrees centigrade and the gases are reheated to 625 degrees centigrade after expansion in the first turbine. The exhaust gases leaving the low pressure turbine are passed through a heat exchanger to heat the air leaving the high pressure stage compressor. The compressors have an equal pressure ratios and intercooling is complete between these stages. The air inlet temperature to the unit is 20 degrees centigrade. The isentropic efficiency of each compressor stage is 0.8 and the isentropic efficiency of each turbine stage is 0.85. The heat exchanger thermal ratio is 0.8. A mechanical efficiency of 95% can be assumed for both power shaft and compressor turbine shaft. Neglecting all pressure losses and changes in the kinetic energy, calculate 1. The thermal efficiency, 2. The work ratio of the plant, 3. The mass flow in kg per second. Neglect the mass of the fuel and assume the following. For air, Cp of air is equal to 1.005 kJ per kg Kelvin and gamma is equal to 1.4. For gases in the combustion chamber and the turbines and heat exchangers, Cp of gases is equal to 1.15 kJ per kg Kelvin and gamma is equal to 1.33. First we understand the problem. Here a gas turbine plant, the air is compressed in two stages and expanded in two stages. The compressor are run by high pressure turbine. The generator produces the power output from the low pressure turbine. Between the compressors there is an intercooler and the air from the high pressure compressor is heated by heat exchanger from the exhaust gases from the low pressure turbine. Now the air from atmosphere at pressure P1 and temperature T1 is entering into the low pressure compressor. It is compressed to stage 2 at P2 and T2 dash. And in the intercooler it is cooled to temperature T3 while maintaining the pressure constant P3. Then in the high pressure compressor it is compressed to pressure P4 and temperature T4 dash. Then in the heat exchanger, it absorbed the heat from the exhaust gases from the low pressure turbine to T5 and in the combustion chamber the air is burned with the fuel supplied so that the temperature increased to T6 but the pressure is constant. And in the high pressure turbine it is expanded to T7 and T7 dash. The work of high pressure turbine is used to run the compressors. The exhaust from the high pressure turbine is again heated at constant pressure to the temperature T8. Then the exhaust gases are expanded to state point 9 where the pressure P9 that is equal to P1 and the temperature T9 dash. Now this exhaust gases from the low pressure turbine is passing through the heat exchanger where it transfers some amount of heat to the incoming air from the high pressure compressor. So this layout is given by temperature entropy diagram where the air at the inlet temperature and the pressure is compressed in a low pressure compressor to state point 2. Then it is cooled by intercooler to state point 3. Again it is compressed in a high pressure compressor to state point 4 dash where this 4 dash to 5 dash is the heat exchanger. Then from 5 to 6 is the combustion chamber 1. From state point 6 it is expanded in a high pressure turbines to state point 7 dash. Again it is heated by the reheater to state point 8. Then it is expanded through a low pressure turbine to state point 9 dash. Then the heat is transferred by heat exchanger in state point 9 dash to 10. So the given initial temperature T1 is equal to 20 degrees centigrade, that is equal to 293 Kelvin, and high pressure turbine drives the compressors. Low pressure turbine drives the generator. The temperature of gases in the combustion chamber 1 T6 is equal to 625 degrees centigrade, that is equal to 898 Kelvin. Then the reheat temperature T8 is equal to 625 degrees centigrade, that is equal to 898 Kelvin. Then compressor having equal pressure ratio and perfect intercooling. Then efficiency of the compressor is equal to 0.8. Efficiency of the turbine is equal to 0.85. Heat exchanger thermal ratio, that is effectiveness, is equal to 0.8. Mechanical efficiency is equal to 95%, that is equal to 0.95. Neglect all pressure losses and kinetic energy. Then Cp of air is equal to 1.005 kilojoule per kg Kelvin. Gamma of air is equal to 1.4. Cp of gases equal to 1.15 kilojoule per kg Kelvin. And gamma of gas equal to 1.33. Find one, overall cycle efficiency of gas turbine. Second one is work ratio. Third one is mass flow in kg per second. For finding this, overall cycle efficiency is equal to work net divided by heat supplied. Here work net we are getting work of L pressure turbine, and heat supplied is heat supplied at combustion chamber 1 plus heat supplied at the combustion chamber 2. Then this work net is equal to work of low pressure turbine is equal to mass of gases multiplied by Cp of gases into T8 minus T9 dash. Per unit of mass is equal to Cp of gas into T8 minus T9 dash. You can take this one as equation 1, this one as equation 2. And heat supplied is equal to heat supplied at combustion chamber 1 plus heat supplied at combustion chamber 2. That is equal to, from the diagram, heat supplied T6 minus T5, T8 minus T7 dash. That is Cp of gases T6 minus T5 plus Cp of gas into T8 minus T7 dash. This is equation 3. Then the second question is work ratio is equal to work net over the work of the turbine, that is equal to work of low pressure turbine over the work of high pressure turbine plus work of low pressure turbine, that is equal to equation 4. So we know the work of low pressure turbine can be obtained from equation 2. Work of high pressure turbine is equal to Cp of gas into T6 minus T7 dash. That is equation 5. The third question is mass flow rate into work of low pressure turbine is equal to power output of the turbine, that is 5400 kilowatt. So this work of low pressure turbine we can be obtained from equation 2. In this question, what are the parameters that we need to identify? We know that T8 they given and T6 they given. So remaining unknown terms for this problem, so we have to find the pressure and temperature of all points, that is P1 to P10 and T1 to T10. Substitute the corresponding equations, we get the answer. First we take the isentropic process 1 to 2. We know that T2 by T1 is equal to P2 by P1 whole to the power gamma minus 1 by gamma, and they given that equal pressure ratio, that is P2 by P1 is equal to P4 by P3 is equal to root of P4 by P1, that is equal to root of 9 is equal to 3. So we get T2 is equal to T1 into P2 by P1 whole to the power gamma minus 1 by gamma, that is T2 is equal to 293 multiplied by 3 whole to the power 0.4 divided by 1.4, that is equal to 401.04 Kelvin. Now we know that isentropic efficiency of compression is equal to ideal compression over actual compression, that is equal to T2 minus T1 over T2 dash minus T1 dash, that is efficiency of compression, that is equal to efficiency of compression we know 0.8 is equal to 401.04 minus 293 over T2 dash minus 293. We get T2 dash is equal to 428.05 Kelvin. Then from process 2 dash to 3, they given that perfect intercooling. That means that T3 bringing into the inlet temperature 293 Kelvin. Then work of compressor is equal to work of high pressure turbine multiplied by mechanical efficiency. Work of compressor 1 to 2 plus 3 to 4, that is equal to work of high pressure turbine into mechanical efficiency. So this work of compressor is equal to work of compressor per kg of air, Cp of air multiplied by T4, T2 dash minus T1 multiplied by 2, that is 2 stages, is equal to work of high pressure turbine into mechanical efficiency. Cp of air 1.005 multiplied by T2 dash 428.05 minus 293 multiplied by 2 is equal to work of high pressure turbine multiplied by 0.95. We get work of high pressure turbine is equal to 285.73 kilojoule per kg. That is equation 6. Now we know that work of high pressure turbine is equal to Cp of gas multiplied by T6 minus T7 dash. 285.73 is equal to 1.15 multiplied by this one is 898 minus T7 dash. We get T7 dash is equal to 649.54 Kelvin. Then we know that isentropic efficiency of high pressure turbine is equal to actual expansion over ideal expansion, that is equal to T6 minus T7 dash over T6 minus T7. So 0.85 is equal to 898 T7 dash 649.54 over 898 minus T7. So T7 is equal to 605.09 Kelvin. And we know that isentropic relation between 6 and 7, T6 over T7 is equal to P6 over P7 whole to the power gamma minus 1 by gamma. P6 over P7 is equal to T6 over T7 whole to the power gamma by gamma minus 1. That is P6 over P7 is equal to 898 over 605.09 whole to the power 1.33 divided by 0.33. We get P6 by P7 is equal to 4.89. And the overall pressure ratio is given, that is P6 by P9 is equal to 9. And this can be written it as P6 by P7 multiplied by P7 over P9. That is equal to 9 is equal to P6 by P7 4.89 multiplied by P7 is equal to P8. P8 by P9. P8 by P9 is equal to 1.84. Expansion in low pressure turbine, that is T8 by T9 is equal to P8 by P9 whole to the power gamma minus 1 by gamma. Then T9 is equal to P8 over P8 by P9 whole to the power gamma minus 1 by gamma. This is equal to 898. Here is 1.84 whole to the power 0.33 divided by 1.33. T9 is equal to 771.049 Kelvin. And we know that isentropic efficiency of low pressure turbine is equal to T8 minus T9 dash over T8 minus T9. That is equal to 0.85 is equal to T898 minus T9 dash over 898 minus 771.49. So we get T9 dash is equal to 790.091 Kelvin. We know that effectiveness of heat exchanger is equal to actual heat transfer over maximum possible heat transfer. That is equal to actual heat transfer is T5 minus T4 dash. Maximum possible heat transfer is T9 dash minus T4 dash. 0.8 is equal to T5 minus T4 dash is 428.05 over T9 dash is 790.091 minus 428.05, we get T5 is equal to 717.68 Kelvin. Then W net, that is work of low pressure turbine, is equal to Cp of gases into T8 minus T9 dash, that is equal to 1.15. T8 898 minus 790.091, we get work of low pressure turbine is equal to 124.094 kilojoule per kg, that is equal to W net. Now overall cycle efficiency, work net over heat supplied. Heat supplied is equal to heat supplied 1 plus heat supplied 2. Heat supplied 1 is equal to Cp of gases into T6 minus T5, that is equal to 1.15 into 898 minus T5 717.68, that is equal to 207.368 kilojoule per second. Heat supplied 2 is equal to Cp of gases into T8 minus T7 dash, that is equal to 1.15 898 minus 649.54, that is equal to 285.73. Then total heat supplied is equal to 207.368 plus 285.73, that is equal to 493.098 kilojoule per second. Then efficiency of the cycle is equal to W net over heat supplied, that is equal to 124.094 over 493.098, that is equal to 25.166 percentage. Answer 1. Second one is work ratio is equal to work net over work of turbine, that is equal to work of low pressure turbine over work of high pressure turbine plus work of low pressure turbine, that is equal to 124.094 then 285.73 plus 124.094. Work ratio is equal to 0.3027. Answer 2. Then the third question is mass flow rate. That is, we know that mass flow rate multiplied by work net is equal to power output, that is 5400 kilowatt they given. Therefore mass flow rate is equal to 5400, W net is equal to 124.094, that is equal to 43.515 kg per second. Answer. Thank you.
Subscribe to our channel, like if you're satisfied, and share because it may useful to someone.